All right, welcome back. Hopefully you had a good night yesterday. All right, so last class, towards the end, I had talked about problems that you can have if you try to do computations on a computer as opposed to doing computations by hand. And this problem becomes more and more critical as you look at problems of larger and larger size. And when we try to solve, okay, so let's say we try to solve Ax equal to b, and now let's assume that this A is not rectangular or anything, it's squared. So A is a n cross n matrix, and B is a vector in Rn, and you want to find X. Now, one would like to use some methodology by which you process this data that's given to you, which is this A matrix and this B matrix. You get the X matrix, and what we would like to have is accuracy. We would like to have a result which is as close to the real answer as possible. Another criterion is speed. We would like to do this as quickly as possible. Yeah, I mean, there's no point in having an algorithm which will take days. And when we are having large systems, the third thing is memory or storage. Yeah. So if you have A to be a 50,000 cross 50,000 matrix, that means just feeding in the entries of A itself is 25 multiplied by 10 to the power 8 positions. Yeah. And now if you're going to do some manipulation by which you're going to store another matrix of that same size, well, yeah, that makes it 50 multiplied by 10 to the 8 storage positions. So, you have to be worried about storage also when you're looking at big problems. Okay. About accuracy, the reason for this, I had already started telling you in the last, yesterday. This is because when we try to store things on the computer, there is, the computer has limits, and there's only certain numbers that can be represented in the computer. Yeah. Now, standard formats like IEEE single precision. Okay, so the single precision is 32 bits, which is divided as 24 bits for Mantissa and 8 bits for Exponent. Yeah. Okay, when I say 8 bits, of course, this is binary. 8 bits, one of them is a sign, plus or minus. So exponents can go from 2 raised to 127 to 2 raised to minus 127. Okay. Now 2 raised to 10, that's roughly 1,000. And so 2 raised to 128 roughly turns out to be about 10 to the 38 or so. Okay. And the Mantissa, 24 bits, one of them is sign, so 23 bits. So 2 raised to 23, that's about 2 raised to 23. Well, that's quite big. That's about 10 to the 21, roughly 10 to the 21. Okay. Now, oh, sorry, 10 to the 7. 10 to the 7. Okay. What that means is, in decimal digits, mantissa is about 7 digits. Yeah, an exponent can be 10 up to about 10 to the 38 or so. Yeah, that's for single precision. If one is looking at double precision, there are 64 bits, and of the 64 bits, 53 bits are for the mantissa and 11 bits for the exponent. And so now you can do the math, you know. So double precision, of course, there's a much larger set of numbers you can store. Yeah, but for our purposes, of course, these are too big for me to demonstrate anything, so I will stick to what I was talking about last time, which is we look at mantissa, which is 4 decimal digits, and let's say exponent, okay, let's say 10 raised to 15 to 10 raised to minus 15. Okay? Let's assume this is the computer that we have. What happens is with, you know, single precision or double precision, and that's more, you know, there's the number of numbers available for the computer is much larger there. Yeah. So let's take some 2 numbers. So let x be this number, say okay, and let's take y to be 519,934. All right. How is this x going to be stored in this computer? So the x, the way it's going to be stored is the mantissa is going to be 5211, and the exponent is going to be okay, and this guy is going to be stored as all right. So though x is this number, what is actually stored is 521100. Okay, so there is already an error. Yeah, and the error in this case is 37. We don't talk about error in absolute terms because in this case it was 37, but suppose the number was 52.1137. Yeah, then how would that have been stored? It would have the same mantissa, only the exponent would change. Instead of 6, it would have been 2. Yeah, and in which case the difference would have been that. Yeah, so there is no sense in talking about absolute numbers. We would talk about error in relatively. So 37 is the error for the number 521137. Is that okay? Yeah. And how much does that turn out to be? Okay, so this turns out to be roughly 7. Okay. Yeah. Now, if you look at the second number, that will also have an error. And the error there is 34. And so that error is 34 upon 519934. And that's also roughly about 7. Yeah. So if you look at this, what it's saying is that the error is in the 5th most significant digit, 10 raised to minus 5. That means the actual number and what is stored differ on the 5th digit. Is that okay? Yeah, now suppose we have stored these two numbers and then we want to do various operations. Okay, the four standard operations: addition, subtraction, multiplication, division. All right? When you do that, suppose you multiply x with y. So the actual answer, so this is what the actual answer should be: 270, 956, 844, 958. This is what the real answer should be. Yeah? What do you think is done by the computer? The computer is going to multiply 5211 to 5199. Okay? And then chop off the digits. Okay? And what do you think it would get? Yeah, so x multiplying y will give you 2709. This is okay? Yeah? So as far as accuracy is concerned, okay, the accuracy, it is going to be accurate for the first 4 digits. Yeah, but the error, as you see, is this large number. Okay? But if you're thinking in terms of relative error, it is this 56, whatever, 844958 divided by this whole thing, and that is still something in the range of 10 to the minus 5. It's in the 5th digit that there is a difference. This is okay? Yeah, and this is not very surprising because, you know, if you have to multiply these two numbers, how does one multiply these two numbers? Yeah, the way we are taught at school, that's one way to multiply it. But as you know, the various languages that human beings parse, some of them we write from left to right, the others we write from right to left. Yeah, in school we have been taught 4 multiplied by this thing you write down, and 3 multiplied by this thing you write down, and so on. But it is easy to see that if you had multiplied 5 to this first, and then 1 to this, but arranged it the other way and taken a sum, you would get the same result. Huh? Yeah, and so when you are doing most significant bits, multiplying most significant bits, your most significant bits are going to be accurate. Is that okay? Yeah? So multiplication is quite stable. Yeah? In the same way, if you do division, when you divide this number by this number, you get 1 point something. Yeah? But what is stored if you divide, again you get 1 point something, and if you check the results, you would find that that is also roughly accurate. Okay? If you were to add these two numbers, then the result, will it be accurate, first 4 digits? No? Why not? So what is the real addition? X plus y will turn out to be how much? Yeah? That's the real addition. And if you add these two, what do you get? 1, 3, right? Is this fine? I mean, I add these two, I'll get 0, 1, 3, 1, 3, 0, 1, but then I have to put it in mantissa, so it moves there, 10 raised to 7. Is that okay? So addition is not a problem. What about subtraction? If I subtract these two numbers, I get 2, how much is that? 1. Yeah, this is the difference between these two. 1203. If I subtract these two numbers, uh, 2, 1, 0, 0, yeah? And this is going to be stored as ten raised to, so 2 less, yeah? Is there a problem? Is there a problem? Well, there is a problem, because what is stored now is this 10 raised to 4, and this is the real number. This real number, if we had directly stored, we would have got yeah. So the accuracy is no longer on the 5th digit, but we already have a problem on the 4th digit. This is okay? Yeah, I can manipulate these numbers slightly and I can make it worse. This is okay? Yeah? So as it turns out, the addition, subtraction, of course I could have talked about this as being addition and this number as a negative number. Yeah? So addition and subtraction are the dangerous guys, not multiplication or division, as one would expect. Okay? The things that we learned first, they are the dangerous guys. Yeah? So, okay, there's nothing better the computer can do when it is given this problem. Yeah? And this inaccuracy would turn up irrespective of, I mean, you cannot correct this inaccuracy. Yeah? And in fact, what one has to realize is that this inaccuracy is because of bad data. Okay? So whenever you have an algorithm, there are two things involved. The algorithm should be good. Yeah? But the algorithm being good is not good enough to guarantee the correct answer. The algorithm should be good and the data should be good. In that case, you would get a good answer. If the algorithm is good and the data is bad, there is no guarantee. If the algorithm is bad, then of course. Is that okay?
Data is not in our hands.
Data is not in our hands. So what you should try and do is try and only do operations which, given good data, will guarantee a good answer. Yeah, given bad data, there is nothing you can do about it. This is okay? Yeah? So one of the things that one wants to do when you design algorithms is try and get algorithms which are good. And what I mean by algorithms which are good is, given good data, it will give you an answer which is accurate. Okay? And of course, along with accurate, it has to be fast, and memory usage must be as minimal as possible. All right? So let's go back to solving this Ax equal to b. And yesterday Professor Ghorpade talked about how to solve this. Yeah? So let's try and solve a simple problem. Let's say 2, 4, 6, 4, 6, 0, 2, 5, 2, 1. Okay. Of course, when you're given this problem, 3 cross 3, just invert the matrix. Yeah. And so x1, x2, x3 is A inverse B. Yeah, you're done. But that is because it's a small matrix and calculating the determinant, there's no real overhead. In fact, yesterday Professor Ghorpade did mention these various definitions of determinant. It turns out that if you have to actually calculate the determinant, you require several operations. Yeah. So whatever I was talking about here was this floating point representation of numbers, and each addition, subtraction, multiplication, division that you do, we count as a flop. Yeah. Flop has different meanings in the movie world, but here it means floating point operation. Okay? So you calculate how fast an algorithm is by talking about the number of flops required to arrive at the answer. Yeah, how many times you need to do a multiplication, a division, and so on. Okay? So when you want to talk about the speed of an algorithm, you talk about how many operations you need to do. Now, if you have to calculate the determinant of a matrix, the way the determinant is defined, it requires an n cross n matrix requires about n factorial flops, roughly. Yeah. Now, if you imagine a matrix which is 5,000 cross 5,000, that is prohibitively large. Yeah. So there is no way you are going to calculate determinant. All right. And so inverting the matrix is not a solution, but of course inverting the matrix is a solution for this small problem. Yeah. But yesterday something was told about how to do this, which was row operations. Yeah. You did Gaussian elimination. Yeah. Okay. So how did you do the Gaussian elimination? What did you start with? Yeah. So you tried to make this 0. Yeah. And so what you did was you multiplied the first row by 2 and subtracted it from the second row. Yeah. And the process gave you 2, 4, 6. And when you did that subtraction, you got here 0 and minus 2, and this minus 12. Minus 6. Yeah, that's the first thing you did. Yeah? Minus 8, is it? Oh yeah, sorry. Yeah. Okay. Now note that this you obtain from here by an elementary operation. Yeah, and that elementary operation is essentially multiplying by this matrix yeah. If you multiplied this matrix to this, you got this. Okay? And then you did an elementary operation to make this guy 0. Yeah? And that would be and what you would have is 0 minus 3 minus 5 okay, and then you had to get rid of this guy, which meant you did another elementary operation, and this time you multiplied that by 3 by 2. Okay. As a result, you got this to be 0, 3 by 2. Okay. That's 4 3s are 12, 6 3s are 18, 18 plus, and so this is 18 plus is 13, and ouch, 6 2s are 12, no sorry, 4 3s are 12, 12 positive minus 4, 8. Okay? And this was the process that you did. Yeah, you multiplied by E1, multiplied by E2, multiplied by E3, and you got this upper triangular form. And once you have the upper triangular form, it's easy to solve this set of equations because now x3 is 8 by 13. And once you know x3, you can substitute into this equation. So you get minus 2 times x2 is minus 12 times 8 by 13, which you have already calculated, is equal to minus 8. From that you can find x2, and then knowing x2 and x3, you can calculate x1 from the first one. Yeah? If you count the number of flops that is used for doing this calculation, in general for a n cross n matrix, it would be order n squared. Okay? Yeah? Now the point is this good? Is this algorithm good? What do you think? Sorry? Yeah. If the order is large, you'll have some difficulty. Why do you think so? Time taking. Okay. Okay. We will come back to this and we will talk about this later. Yeah. Sorry? Yeah. Number of iterations is equal to number of unknowns. No, that's not true. I mean, it so happened in this case because I am taking a 3 cross 3 example. Suppose you had a 4 cross 4 example, then you had to make the lower diagonal things all 0. You would have had to have obtained 6 zeros, though the number of variables is 4. Yeah, I mean, it's 1 plus 2 plus 3 up to n minus 1. Yeah, so that's not true. Okay? All right, so we want to talk about how accurate the result is, which means we have to talk about distance. Yeah? On the real line distance, of course, we know. You just take the first number, you subtract the second number, you have a distance. But we are talking about vectors. Yeah? And therefore, for the vectors, we need to define a norm. All right? Yeah. Okay, so what is this norm? So norm is a function from the vector space to positive real numbers. Yeah, all of you are aware of this norm. Supposed to satisfy some properties. So what are the properties? Yeah, norm of a vector is greater than 0 and okay, greater than equal to 0, and norm B equal to 0 implies sorry? Ah, yeah. Okay, next one. If alpha V, if you take the norm of alpha V, where alpha is a scalar multiplication, this should be equal to okay, homogeneity is the name that's used for this. What else? Yeah, the triangle inequality. So if V1 and V2 okay. Examples of norms? Yeah, the standard one is the 2 norm. If you have an x2 norm, or okay, so let's say x1, x2, x3, 2 norm is square root of yeah. There's one norm is yeah. There's the infinite norm. Yeah. In general, P norm is summation defined for P yeah. Okay, this is one whole set of norms. Okay, so the P norm is given by that, and what we will try to do, or what we will try to see, is we will try to see what, for various P norms, what all vectors which have norm 1 look like. Yeah, so for the 1 norm, all vectors that have norm 1, what would they look like? How do they go? Yeah, okay. For the 1 norm, what would it look like? Well, that's what it will look like. Is this clear? Yeah? As far as the 1 norm is concerned, because if you look at that top line, it is x1 plus x2 equal to 1. Yeah? For the 2 norm, what would it look like? It's a circle. Yeah. 3, 4, 5, 6. Okay? Is that fine? So as you change the norm, you get these sets, and these are whatever we are drawing as a boundary is all those vectors which have norm 1. And so if you want to think of all the vectors which have norm less than equal to 1, it's the inside of whatever was the boundary. Yeah, and that's what one calls unit ball. So under various norms, these are the unit balls that you would get. Okay? So why is this limit on the P? Yeah. So what happens if it goes inside? Yeah. Yeah, that's right. So suppose we look at now what's happened? Click. No. So that's 2, 1.75, 1.51. Yeah. Essentially what's happening is you lose convexity. Yeah. And as it turns out, this convexity is this next big property that you require in most things that human beings do. Yeah, after linear algebra, next is convexity. Yeah, you lose convexity, triangle inequality no longer holds. Okay? And therefore, that's why for P less than 1, we don't have that to be a norm. Can I have the lights back, please? Yeah? Okay, so this is the norm as far as vectors are concerned. But we want to measure things as far as even for matrices. Yeah, so we want to put what's called a matrix norm. Yeah, the set of all n cross n matrices is also a vector space. Okay, so we want the norm to be defined on the set of matrices, and it should obey these rules. That means this should be satisfied, homogeneity should be satisfied, triangle inequality should be satisfied, and we want one more condition to be satisfied. And that condition is, okay, so we are talking about matrices, the product of two matrices. The norm, you want that to be less than okay. Yeah. Now, this whole theory of matrix norm, of course, just goes on and on. But what I'm going to do is introduce what are called induced matrix norms. Yeah. Now, what do I mean by induced matrix norm? Okay. So suppose we are looking at this matrix A, which is a R, okay, n cross m matrix. Yeah, not necessarily square, n cross m matrix. So what do we have here? A acts on an X, and this product AX belongs to Rm. Okay? X belongs to Rn. Yeah? Now on Rn and on Rm, let's assume we have used the P norm. Okay? Then I define the induced P norm of the matrix A as maximum for X which is non-zero, yeah, non-zero vectors, of the P norm of AX divided by the P norm of X. This is okay? Is the definition fine? All right. Now, if X maps to AX, what does K times X map to? K times AX? It's a linear map. Yeah? And so if you look at this, then for kx, this would become mod k mod ax yeah, you can cancel the k's. So what that means is we need not look at all the vectors, but we can look at all the vectors p which has norm equal to 1 and take the maximum of ax. Is that okay? Yeah? So the norm, the pth norm of A is defined as this. Yeah? One way to interpret this is given x of norm 1, A acts on it, you get a vector, and you want to know the maximum magnification that you have got. Is that fine? Yeah? So the matrix norm is the maximum magnification that you've got. All right? This is okay? Yeah, so maybe quick quiz. So here is a matrix A, 2, 1, 3, 5, 7, 2. And suppose we are looking at 1 norms. What's the 1 norm of this matrix? $20? How do you get that? Adding elements. You mean you've added all of them? No, 20 is not the norm. Remember, for the 1 norm, what do you have to do? You have to take all vectors x which have norm 1, and this is a 3 tuple. Yeah, if you have a 3 tuple with norm 1, what does that mean? So the 3 tuple is alpha, beta, gamma. Yeah, and you want mod alpha plus mod beta plus mod gamma to be 1. So what would it be? Seven? No, it turns out that it will be 9. The 1 norm of this matrix is 9. What you have to do is look at 1 norms of each of these columns. 1 norm of this one is 3. 1 norm of this one is 8. 1 norm of this one is 9. Okay? Now, suppose you take something like this, alpha, okay, suppose you took 1, 0, 0, that's a norm 1 vector, and that would give you an image which has size 3. Right? If you took 1, 0, 0, that maps to 2, 1, and the norm of that is 3. If you took 0, 1, 0, that would map to 3, 5, which has norm 8. Now, if you take alpha, beta, 0, this is going to be a convex combination of these two, if they both are positive. Okay? So you get the sum of these two, convex sum of these two, and that is going to be a number which is going to be less than 8. This is okay? Yeah? So this is going to be alpha and this is going to be 1 minus alpha, for example. Then what will that map to? It will map to alpha times this and 1 minus alpha times this. So now when you take the sum of that, it's going to be less than 8. Yeah? So the way you find the 1 norm is find the 1 norms of each of the columns and take the maximum. This is okay? What would be the infinite norm of this? Seven? No. No. Infinite norm will be? No. So the infinite norm here would be 12. Yeah. Now what do you mean by saying x infinity has norm 1? What does it mean? So what you would have, at least one of the entries must be 1 or minus 1. Those are precisely the vectors which have infinite norm equal to 1. At least one of the entries must be 1 or minus 1. Yeah? Other ones can be anything. 1, 0, 0.5, norm of this is 1. 0.75, norm of this is also 1. Is that okay? Yeah? So for this, the best guy to use is 1, 1, 1. So when you use 1, 1, 1, you get the sum of all this, which turns out to be 12 and 8, and the infinite norm of this is 12. Yeah? The best way to find the infinite norm is take the sum of the rows, the 1 norms of the rows. So take row sums. Row sum here is 12, row sum here is 8. The maximum amongst that, that's the infinite norm. Okay? 2 norm? Well, 2 norm, there are enough people who will discuss this later. Yeah? For 2 norm, you need singular values, which will be discussed further down the workshop. So the 2 norm is going to be the largest singular value of this. Yeah, how it is calculated and all would be done. All right? Okay. So now that we have these norms, we go back to trying to solve that Ax equal to b, and it turns out that we want to measure what good data is. Yeah? And the way you measure the good data, that means given A and B, the way you measure whether that data given is good or not is by checking what's called the condition number of the matrix A. Okay? Good data means the condition number should be good. Okay? Now, how is the condition number defined? So, suppose we are trying to solve Ax equal to b. Yeah? But let's assume that What we really solved was A, okay, what we really solved was, let me put a tilde here, B plus delta B. So B was not accurate, but what we solved was the exact solution for this equation. Yeah, there is an error in B. Okay? Now this error can be thought of as okay. So Ax plus delta x is giving you B plus delta B, and this x of course is the actual solution. All right. Now if you subtract the original equation from this, then you end up getting A times delta x must be equal to delta B. Okay? Yeah. Of course, we are assuming A is a n cross n matrix and it's invertible and so on. So delta x can be thought of as A inverse of delta B. Okay? Now the way we define the matrix norm, A was defined as maximum, right? So what happens is, what can you say about this, this, and this? Okay? Yeah, because we have insisted on the sub-multiplicative property, that must be true. Okay? So here we take norms. We have norm of del x must be okay? This is fine. The original equation Ax equal to B tells us yeah. Okay, so the product of these two is still an inequality, and then I slightly rearrange, and I will end up getting delta x by x is less than equal to norm of A inverse okay. Now if you think of this, this is the relative error in the solution. Yeah. This is the relative error in the data. Okay. And this here is the condition number. This is okay? Yeah, but there are ways to approximate. That is a, yeah, so correct. But you can estimate A inverse without finding A inverse. Yeah, there are ways to do that. Okay? Sorry? No, so the condition number is defined as norm of A multiplying norm of A inverse. So what this is relative error in the solution is less than condition number times relative error in the data. Okay? Yeah? Yeah, we only estimate.
We are not interested in inverses and we are not interested in exact condition numbers. We only do estimation of condition. Calculating exact condition number is again an enormous amount of work and probably not worth it.
Yeah. Yeah, we only go by estimates. We don't, we just want to check whether the given data is good or bad. Yeah. Okay. So this here is a condition number. So let's quickly run through some properties of this condition number. So condition number must always be greater than 1. Is that clear? Is that clear? Condition number should be greater than 1. Norm of identity is going to be 1, right? Because identity gives you a vector of, yeah, unit norm, it will give you a vector of unit norm. So identity is 1. This is okay? Condition number greater than 1? Because if you have a matrix whose largest magnification is smaller than 1, then its inverse, all magnifications must be larger than 1. Is that okay? Yeah. In fact, another way to look at condition number is largest magnification, yeah, the norm of A was the largest magnification. So the norm of A inverse is going to be 1 upon the smallest magnification. This is okay? Yeah. A takes a vector, A takes x to y. Yeah. A inverse is to x, no? Correct? So if this magnification, so the norm of y was greater than the norm of x, yeah, then when you normalize that to 1 and you look at A inverse, what will you get? You will get precisely the inverse, right? Yeah. So if you wanted to calculate the norm of A inverse, it must be the largest magnification of A inverse. But that's equivalent to saying it's the reciprocal of the smallest magnification of A. This is okay? Yeah? All right? So this is another interpretation for condition number. Yeah. Now, of course, if A was singular, then what would be the smallest magnification? It will be 0. And therefore, the condition number would be infinite, not defined. Is that okay? And of course, in that case, A inverse doesn't exist. So this definition sort of falls through. Yeah, but that is the case where the condition number is infinite, means it's the worst situation. So the condition number is always going to be greater than 1. Okay? Second one, condition number of, some C times A, what's that going to be? This is going to be equal to condition number of A. This is okay? Yeah? Because C times A, when you take A inverse, you'll get 1 by C times A inverse. So the C's cancel. Yeah? What are the properties of condition number? और क्या property है? Okay, let's hold that. Going back here, let's assume that the condition number let's assume condition number is 10 raised to 5. Okay? What does this inequality tell us? That if you had an error, yeah, small error, let's say del B by B, small error, what is small? Let's say this was millis, yeah, then the product of these two is 100. What that means is that the error as far as the solution is concerned, well, it could be as large as 100 times the magnitude of the original solution. Yeah, I'm not saying it happens every time, but that's the limit that's given to you. Okay? On the other hand, if the error was then this product is 1 by 10, which means the error that you can expect is about 10%. I mean, this is of course a maxima. Maximum error that you can have in your calculation is about 10%. This is okay? Yeah? So now I remember another one. Suppose you have two matrices AB, condition number of AB, okay? Actually, I guess one has to put that. Okay? Yeah? All right. So now we go back to what we are doing there. So suppose you are given to solve Ax equal to B, and you have a condition number. Yeah? When you multiply the matrix by this matrix E, what are you doing? The new equation So let this be E1, E2, E3. Yeah, so E1A x equal to E1B. Now we have to look at the condition number of E1A. Yeah? And what can you say about the condition number of E1A with respect to the condition number of A? Less? It depends on the condition number of E1. Huh? This is okay? So if the condition number of A was 10 raised to 5 and condition number of E1 was 10 squared, then what you're saying is condition number of E1A can be 10 raised to 7. Of course, we are not guaranteeing it is 10 raised to 7. This is okay? Yeah? So, what should we really do? Okay, so this is essentially you have data and you try to fiddle around with the data, you soil the data in the process. Yeah, so you could have good data and you try manipulating this data and you could actually make it worse. Yeah? This will be less than or equal to this provided this condition number is as close to 1 as possible. Is that okay? Yeah? Therefore, the condition numbers of these elementary matrices must be as close to 1 as possible. This is okay? Yeah? And what this translates to is, you see these numbers that we put in 2, minus 1, minus 3 by 2, they were the pivots. They were the amount by which the pivot was multiplied. They should be as close, in fact, they should be as small a number as possible. Yeah, right now the condition numbers of E1, E2, E3 are all greater than 1. Okay? But you want to keep the condition number as small as possible of these elementary matrices so that your original data does not get soiled too badly. Okay? Yeah? What would be a good way to guarantee that the data stays as pristine and pure as what was given to you? Yeah, if you make the condition numbers of this E1, E2, E3 all to be 1. Yeah? So that brings us to the question, which matrices A have condition number to be equal to 1? Identity matrix, of course, has condition number equal to 1. Which other matrix has condition number equal to 1? Yeah, rotation. Yeah. Yeah, if you rotate something, Yeah, the vector has the same norm. This is okay? Rotation, that's what it does. Is it fine? Yeah, and rotation, the matrix is given by cos theta this is the matrix that will rotate a vector in a plane by an angle theta. Yeah, given any vector of some size, it will get rotated by an angle theta. The norm will remain the same. Okay? Yeah? That's fine? All right, so if that is the case, then let's do the converse. So suppose you have a vector like, say, 1, 2. Yeah? You can keep rotating this until the second entry becomes 0. What would be the first entry? Norm of this vector. Yeah, which is root 5. Okay? What is the amount by which you have to rotate to do this? This is the vector 1, 2. We have to rotate by this amount. Huh? Okay? And what is cos of that angle? It's 2 by root 5. Yeah? So this rotator matrix you can do by 2 by root 5, 1 by root 5, minus 1 by root 5, 2 by root 5. And if you do that, you can convert the 1, 2 to root 5, 0. This is okay? Yeah? All right. If that's the case, we want to solve this. Take this vector 2, 4. I can rotate it so that it becomes something 0. Yeah? Is that okay? Let me call that rotator Q1. If I multiply this equation by Q1, do I soil the data? No. Okay? And the end result of that rotation would be this 2, 4 gets swung around to something like 16, 18, root 18 by and 0. Yeah? 16 for root 20. Root 20 and 0. Okay? But the same rotator is of course acting on 4, 6 and this thing, so you get something, 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 2, 1, 1. Okay? Now I take root 20 and 2 and rotate that. All right? So now what do I get? I'll get root 24 here, 0. Okay? And now these two I rotate so that this guy becomes 0. Yeah? So I get this matrix here. Now what I'm saying is Q1, Q2, Q3 are all rotators. Multiplying A gives me this matrix R. These rotators are orthogonal matrices. Its transpose is its inverse. Yeah? And so A is Q1 transpose, Q2 transpose, Q3 transpose, R. All of this together I call it Q, and this is what's called the QR decomposition. Okay? Yeah? And the rotators that we are talking about, another name for it is Gibbons rotations. Okay? Yeah? Of course, when you have a huge matrix, how many rotators do you have to use? That looks like a very huge number. Yeah? But of course, if you have a huge matrix, but it's sparse, there are very few elements around, then these rotators are good to do a minimal number of things. You just pick out that rotator and get rid of those non-zero elements to make it upper triangular. And this, of course, Professor Soman would elaborate on. Is that okay? Yeah? Is there some other way to do all this? So there's some other way to do all this. And, you know, we are talking about guys, matrices who have condition number to be 1. Rotators are one set, and another set of matrices which have that property are the reflectors. Yeah. So, which one? This is about X, no? So this, for example, shows us reflection about the x-axis. Yeah? Some vector like that gets reflected to that about the x-axis. Something like that gets reflected to the one down. Okay? This is okay? Yeah? So what the reflection does is, for the line that is given, there is no movement. So on the x-axis, if the vector was on the x-axis, there is no movement. But if there was something north of the x-axis, it went south of the x-axis. All right? But we could have this for, this is the reflection, above the general line also. Yeah, it reflects to something like that. And this is say 90 degrees, it reflects to something below. Okay, if you have a vector like that, it reflects to something like that, and so on. This is okay? And if you have something along the line, then the reflection is again along the line. Yeah? So what we are going to do is the following. This is the original equation that we have. What is the reflection going to do? It's going to send a vector to another vector of the same norm. Right? So take this first column here, 2, 4, 2. Yeah, what's the norm of this vector? 16, 4, 24, square root of 24. Okay? So we want a reflector which will do this. This is okay? If you get a reflector which will do this, then you make that reflector act on this, and you will end up with root 2400, and these guys will all get modified. Okay? After that, these two together, whatever is the norm, so you want this star star to go to some tick 0. A reflector that will do that. Okay? And you do that, we are back to the triangular system. Yeah, so instead of using rotators, you could use reflectors. Yeah. Of course, the name Householder transforms is what these guys go by. Yeah? Okay, let's fix this. How to get this reflector? Yeah, you need to consider a surface which will reflect. How do you find this surface? If you have one vector like this and you have another vector like this, both have the same norm, they should be reflected about the bisector, right? How do you define this thing? And you have to remember that this is in higher dimensional space, so this is n-1 dimensional. So how do you define an n-1 dimensional surface? A hyperplane, if you like. How would you define it? By talking about all vectors which are orthogonal to some vector, right? And how can one find this vector? Is that okay? So if I have to go from here to here, I take the difference of these two, and I take the plane to be everything which is orthogonal to it, and I will reflect over that plane. This is okay? Yeah? So, yeah, so I'm out of time. So before I finish off everything, remember that first set of things that we did, and we had multiplied by this E1, E2, E3, and so on. These matrices were all lower triangular matrices. Yeah? They were all lower triangular matrices. That means they all had structures like that. Product of two lower triangular matrices is a lower triangular matrix. Inverse of a lower triangular matrix is a lower triangular matrix. Is that okay? The inverse of this is all right? Inverse of that okay? So we had all these things. It's a lower triangular matrix acting on A, and it gave you a matrix like this. Upper triangular. You call this U, you invert this, call that L. A has a LU decomposition. Okay? Yeah? And when you were doing these calculations for the LU decomposition, for example, you were using these multipliers like -2, -1, and so on. See, -2, I can store here because this entry is supposed to become 0. Yeah? And so I can save on storage. Each time I do this calculation, I store those things here, the multipliers here, and therefore I don't use any more memory than what I have already used. Okay? So ultimately what I want to say is when you try to solve this Ax equal to b, there is some data given to you. You have to coax out the best possible answer. And you have to do this with what we famously call jugaad. Some sort of jugaad you have to do. Yeah, and there is all kinds of hacks that you have. Yeah, what I have given you is a broad picture. Once you dive into it, there is all kinds of, very minute kinds of hacks which will guarantee that things that come out are as good as it can be. Yeah. And unfortunately, we tend to trust the computer a lot, but that's not really done. For example, this afternoon when you go for your lab session, here is a problem that you can try to solve. How much should you get? What will you get? What is the answer of this? 0, right? Yeah? You try it today when you go for the lab. Oof. It's not going to give you 0. Yeah, it will give you something like 2.2 multiplied by 10 to the minus 16 or something. Yeah? So even a simple thing, mental problem, is not solved accurately by the computer. So to trust it without actually knowing what is coming out is a dangerous thing to do. Yeah? There is a belief that you can do a lot of manipulations of the computer, and whatever comes out of that, you can claim that that is true. Well, you can do that provided you have taken all the precautions that's required. Yeah. Jumping in without taking the precautions is no good. Yeah. So there's one end of the spectrum where people believe just in simulating, and there's the other end of the spectrum where people believe just in building theorems. Both of them are extremist views. Yeah. Has to be, you have to walk the middle path. Okay? Hope I conveyed something. Thanks.